Welcome back. I've got a really interesting experiment for you today, and one that you can try at home. It uses really simple apparatus. All you're going to need is a ruler. So, find yourself a ruler, and you need one that's quite flexible, quite bendy. In other words, its stiffness is quite low. And what we're going to do is we're going to shake the ruler and see what happens when we shake it with one hand. So, take the ruler and hold it up vertically in one hand and just move it from side to side. Now, I know it's obvious what happens here. The ruler moves piecemeal, the whole thing moves from side to side. But what we need to do is increase the frequency of the oscillation of your hand. And what you'll notice is, as you turn the frequency up and up and up, the ruler begins to waggle. Okay, well, you might think that's fairly obvious, but what happens if you shake it at an even higher frequency? It hardly moves at all. At a low frequency, it moves from side to side. At one particular frequency, it moves like mad, and at a very high frequency, it hardly wiggles. Something rather strange is going on here, and I'm going to need to explain it. So, let's just say what we noticed. Moving it with a low frequency, the whole ruler moves from side to side. Moving it at a very high frequency, and the top of the ruler hardly moves at all. But get the frequency just right, and it really waggles from side to side. And there's something I'd like you to notice, that if I get it moving from side to side really well, I'm not actually moving my hand very much. I'm certainly moving my hand much less than when I do this. And yet at this particular frequency, it really likes to shake up and down. And this is an example of resonance. Okay, you've got to admit that I think you know about this. You probably, when you were younger, put a ruler on the end of the desk and twanged it to annoy teachers in your class. And this is a similar sort of idea. The length of the ruler over the desk was exactly the same as the length of the ruler in my hand, and when it vibrated most with the biggest amplitude, that's the same frequency it vibrates at when you twang it over the edge of the desk. So, let's do a bit more explaining. So the ruler has a natural frequency, a frequency it likes to oscillate at. The natural frequency is when it's at resonance. In other words, the ruler is really good at taking energy out of my hand and putting it into its own vibrational movement. You might remember the video I did with the teddy bear on the loudspeaker, and get the frequency right and the arms waggle up and down. So we now know that a ruler has a natural frequency, a frequency at which it likes to oscillate, it likes to take energy from my hand. Get the frequency wrong, and it doesn't take energy from my hand to cause vibration. Get the frequency too high, and it's very ineffective at removing energy from my hand. But get it just at the natural frequency, and even if your hand's moving very, very little, it will waggle a great deal. So why do we need to know about resonance? Well, you can see resonant effects all over the place, and sometimes they're really good news, and sometimes they're extremely bad news. An example is a tall building in an earthquake. If you've got a tall building like this and the earthquake is very low frequency, the building will basically move piecemeal. It won't encourage the building to crack particularly. If it's a very, very high frequency earthquake, the building might waggle around a bit, you might feel it, there might be some damage done. But if the earthquake is exactly at the natural frequency of the building, this is extremely bad news, and the building is going to collapse. So we need to know about this, and we need to design large structures so they do not have a resonant frequency near to any frequency they might be oscillated at. Now, get your design wrong and it can have really, really serious consequences. One of the most famous ones, and it's been studied by engineers and physics students alike, is the Tacoma Narrows Bridge collapse. This was a bridge that was built with the same resonant frequency as the vortexes of wind breaking off it. And in fact, it wasn't a particularly windy day, but the bridge was being pushed and shoved at exactly the same frequency as its natural frequency. It went into quite a complex oscillational mode, but the oscillation amplitude was big enough for the bridge to finally break up and completely collapse. It didn't last very long. Anyway, I hope you enjoyed that video and learnt a little bit more about resonance and why at times it can be a really bad thing. So, I look forward to seeing you again next time.